Okay, so here's our topic, the reaction quotient, Q, and here's what our objective is, and what that means is you're given a scenario, you want to be able to tell me what the Q is, what the reaction quotient is. Now, the formula that I'm going to give you is not going to be on your reference sheet. This is not the newest reference sheet, but the Q isn't on there. It's going to be on, it's going to apply to two scenarios. It's going to be found in both electrochemistry and equilibrium. When you look at thermal electrochemistry, you're going to see three Qs, one there, and one there. It's none of them. Sorry, it's the one on the bottom. It's only this one on the bottom. However, it's not going to tell you how to calculate it, so you're going to need to remember how to calculate it. All Qs are calculated as if they were Ks. All right? Now, this is what the reaction quotient is. It's a ratio of products to reactants, all right, and their concentrations, be it gas or molarities. Way to get it is from an equation, and you simply multiply your concentrations. Remember, this is only gases or aqueous things, and you raise them to the power of their coefficient. All right? The topic of Q, when it's in equilibrium, when it's with equilibrium, you're going to use it with two topics. Which way the reaction's going, and with insoluble salts. With electrochemistry, you use it in non-standard conditions. That's like not 1 molar or a few other conditions, like not 1 ATM kind of thing. All right. Now here's an example. Let's say here's my reaction chamber, and I want to know my Q. So I look at these things, and I know that orange is the product. So I say 1,6 because I've got 1 orange and 6 blues. So but little Frito reminds us to use the chemical equation. All right. And if you look at this chemical equation, 2A, that means the concentration of the reactants down here is going to be raised to the 2 power. Right? So it's really 1 over 36. All right. Now in this scenario, these are gases, so we'd use the brackets. So I need to calculate the Q for this one. It's going to be not brackets, parentheses, because it's a pressure. So it's going to be the concentration of R to the 2nd power. My concentration of R is the blue. So there are 1, 2, 3, 4, 5 blues. So there are 5 blues. All right. So that's 5 squared, 25. How many reds? 1, 2, 3, 4, 5, 6, 7, 8. All right. This should be 8. All right, not 5. All right. Divided by the concentration of the reactants, which is this one, just as 1. So 25 times 8 is 200. All right. Now, this is a galvanic, this is an electrochemical galvanic cell, like a battery. Here I've given this thing. Here are my concentrations. Here's my equation. Now, what the Q is only going to be between the things that are aqueous, so the concentration of copper ion and zinc ion. All right, so the other two are going to fall out, and that's what I'm going to have. And here's my concentration of copper nitrate. It'd be a 1-to-1, so it'd be 1.5 divided in the numerator would be 1.5, and the denominator would be 1.5 in that. So my Q is going to be 0.5. All right. Now, what it means is you could think of Q being like greater than 1 or less than 1. If it's around 1, what you means is your concentration of your reactants are around the concentration of your products. If Q is less than 1, it means your concentration of your reactants are greater than your products. And you've got low numbers on top, big numbers in bottom. Now, that's all relative. They could be like low and big relative to each other, not necessarily low and big numbers. All right? And Q is greater than 1, the opposite. I'm going to have greater concentration of products than reactants. All right?